So let's say we've got some polarized material and it's got a total polarization per unit volume which is given by P, and what we want to do is calculate the electric field some distance away. Now what we can do is we can split this material up into infinitesimally small dipole moments given by P, and the separation vector between our dipole moment and our observation point is given by r minus r prime. And what we've already found in the previous section is what the potential of our dipole is, and this was given as by 1 over, and went as the 1 over r squared, so we have 1 over r minus r prime to be squared, and then we had the dot product of r hat dot p, so I'm going to write this out explicitly, so r minus r prime divided by r minus r dash prime dot the dipole moment. Okay, so this is the potential due to just one dipole moment. So all we have to do in order to find the total potential now is to integrate this over the volume. So now what we have for the total will be equal to V of R be 1 over 4 pi epsilon naught by our integral of 1 over r minus r dash prime to be squared for the unit vector by P, so dipole d tau, and this of course is d tau prime. Okay, so this will give us the answer for the total potential due to this polarized material. Now we can take this a little bit further, and what we can do is we can in fact split this up into both a surface integral and a volume integral. So integrating by parts using the divergence theorem, you would have 1 over 4 pi epsilon naught by our surface integral of 1 over r minus r prime to be squared by the total polarization, which would be P dot dA prime, plus our volume integral of 1 over r dash prime to be squared by the divergence of P d tau prime. Okay, and again, the primes here signify that the integration is with respect to the source term. So when we just look at this, what it appears that we have for the surface integral is it's just like the potential of a surface charge. So now we can write sigma b is equal to P dot n hat, where n hat is just a normal unit vector. The second term, it just looks like the potential of a volume charge. So we can write this as rho b, and b here signifies our bound charges, so you can minus grad minus divergence of P. So what this means is that the potential and hence the electric field for a polarized object is the same as that, as will be produced by a volume charge density plus a surface charge density. So what we can do is, instead of integrating over all the infinitesimal dipoles, what we can do is we can find these bound charges and then find the electric field which they will produce. And we do this in a similar way to what we have done for any other volume charge densities, as an example, such as what we did for Gauss's law.